So, guys, where are we? So now we're going talking about dynamic imbalance, right? So remember what we talked about. So this one we're concerned with the horizontal and vertical planes here. And it says when several masses rotating different planes, the centrifugal forces, in addition to being out of balance, forms couples. What do you mean by couple? There's a moment. A system of rotating masses is in dynamic balance where it does not exist any resultant centrifugal force as well as resultant couple. So for dynamic equilibrium, we have to meet the condition of static equilibrium, and that means our MR must be equal to 0. That's what we've done. And now we have a new thing. We have MRL must also be equal to 0. So they just talk about, there's a picture here. There's mass A, B, and they're located on different sides of one is located on the left side of plane of rotation, the other one on the right hand side, and both those centrifugal forces are acting in different planes, and because of this, each mass will try to pull the drum in each direction of the centrifugal force. So this is a dynamic imbalance, right? So we're trying to correct this kind of thing. So what we actually can do, you're going to end up having two masses in different planes, I think, and then we'll end up balancing it. So this is from the N6 textbook, and this is what it basically says here. Consider the masses shown in the figure supported by two bearings. And obviously, balancing to do with the shaft, rotating, and maybe we'll start to expand upon that later on. Even if they're statically balanced, the centrifugal forces acting along different planes. Say a turning moment or couple. Let's say the system is therefore statically balanced in this case, but dynamically out of balance. So this unbalanced moment will cause dynamic loads on the bearings. In order to balance the system, we need to calculate a few things here. So we don't want to talk too much about that. It's also something important which might come up, but if they ask you for dynamic load on the bearings, take the out of balance couple divided by the distance between the two bearings. Obviously, this will be the dynamic loads of the bearings will be equal in magnitude but opposite direction. We've discussed something like that. And also the balance force required with the out of balance couple and the distance between. So these two things might come up, but I'm making you aware if you do see words like dynamic load bearing and the balance force required, or there's ways to find this, but I'm not really particularly focused, but this is more particularly on the dynamic side. So we finally heading into the dynamic realm, and what it basically is, you have balancing of several masses rotating in different planes, and that's what it is, right? And yeah, they're saying the same stuff. If you look at the text at the bottom, and it's, I don't know why is it it's positioned at the side here. I probably didn't actually align it in the middle. I can move that there. Where are you here? I can just move you here. Just increase the size of this. And what this simply is that when a revolving mass in one plane is transferred to a reference plane, its effect is to cause a force of same magnitude, the centrifugal force of the horizontal. So yeah, so we just and there's a length, because what it means is a mass in the one plane is a mass in another plane, right? And there's a length in between them. And what you're trying to just basically do is get two masses to balance this thing, and you'll get the planes. But there something is important about revolving in masses in different planes is that your forces in the reference plane must balance, the resultant must be 0, and the couples about the reference plane must balance, the resultant couple must be 0. So it's important here's a word, a reference plane coming up. There's a reference plane, so we'll talk about this reference plane. Okay, that slide is blank. Oh yeah, I did this. So the two conditions I didn't mention, it's to the forces in the reference plane must be 0, and then so that's a static balance, and this is the dynamic balance. So number 1 is static balance, number 2 is dynamic balance, right? And then going to this is just the explanation of how it's going to work. So once again, we'll both do the analytical and graphical approach. But what's important there, so let's talk to the slide. So if you look at it, that picture there, once again, we've got two images. So focus on the 1B, the angular positions of the mass. So in this case, we have masses, again, as you know, it looks like it's in the same plane, M1, M2, M3, and M4. And they're rotating, right? But if you look at position on number A is 1, 2, 3, 4. But can you notice they're all at different lengths? So they're not actually acting in the same plane. So they're not. So when I say the same plane, normally, if you look at position 1, that is normally all masses are rotating in that plane. But here, they're rotating in different lengths away from a reference plane, which is in this case L. We'll talk about that. So one is L1, and one is L2, and one is L3, one is L4, and those are that M or L. That is a length. So they're not in the same. They're not all rotating on plane number 1, so to say. They're rotating in plane 1, plane 2, plane 3, plane 4, arguably, right? So maybe I should I'll sketch something like that if I can possibly. So just imagine like a line like this. So when I say different planes, like this is now like a z-axis. Just bear with me. Let me just figure out how I'm going to do this. Okay, maybe this should be shifted over here. It's one plane, another plane, and I'm just going to go 3 planes here. So normally we're sitting with another color, black, no, blue, red, no, blue, green. So we're sitting on a mass here, and remember this is just treat this as like a vertical line here, like that. And we're sitting with another mass there and another mass there. This is all in one plane, right? But now in this case, they're not sitting in one plane now. There's a one mass there. In this case, another mass going like this, and another mass going like this. Does it make sense to what does it make sense when I'm talking about different planes now here? You guys get what I mean? It's not in the one side, it's now all over the shaft basically. Hope you guys understand that. Austin, Jason, you guys get that? So it's in different planes now. Is no one getting that concept of different planes or what I mean? Anyone? Hello? Yes, okay, thanks. So now what happens is, wait a minute, slide now. So like I said, initially we're in one plane, right? So let me just go back. So normally sitting over here, let me just draw the red line like this. We've got an axis like that, and we have masses revolving around here. So there's one there. This is what we just did now, and another one here, and another one there. But now we have masses in all the other planes. Okay. So what we normally do, we have to take a reference plane. And what typically happens, because if you remember the dynamic balance, what I said, thank God for technology, I can explain this so well, is that we are concerned on the top half of the tire as well as the bottom half, hence the vertical or vertical. In this case, we also concerned about the left and the right, so we vertical and horizontal imbalances. So we've got two dual plane balancing, so we've got two masses we need to sort out now. And our question typically states, so if you can see on this image that here's L and M, those are the balancing masses. So what we normally look at is how far from a particular reference plane do we position those masses. So normally we take the reference plane from one of the masses, but obviously we can take it from another mass. But obviously with more time as you go along, you get used to it. But let's say plane M is at the distance LM from the reference plane L. So in this case, they chose L. And anyway, you're going to have something similar. I'll get to that now. So you have plane 1, in this case, your masses, your radius, your MR column. But now what's new is L, so the distance from the reference plane. And then you have the MRL, which is called your couple polygon. So one you see is your couple polygon, and then your force polygon. So now you have two graphical things basically. And you normally start with your couple polygon, and once you have a couple, some stuff of your couple, the particulars you found there, and you find, then you got your force. But they follow the same principle in the sense of the angles. Obviously, there's no angles over here. Sorry, the angle's missing there. But it's also head to toe. It's essentially the same thing. So remember, for dynamic balance, we need to resolve that moment or that couple, because it's creating another bending moment on the shaft, and then of course we have to do dynamic and static balance, and that's the force balance. And then basically, for complete balance of the rotor, the resultant force and resultant couple both must be 0. So here was the initial one, the mr1 omega squared, and now we have mr1 omega squared, L1, L2, L3. Basically the same setup, and it's essentially identical to what is this, to the force one, but we just have to include, instead of mr only, it's a sum of mrl with the same angles. Yeah. So then this is basically explain the math. So one's in the vertical direction, one is in the horizontal direction. And what we can do now is we sum them up. We can square them if you want, exactly what we did before, and we can find this. But this one must be aware when we're doing this, right? You find one for how do I say? There is the left plane. There's plane M, and there's plane L, and there's plane M. So you first normally find M, the one away from the reference plane, and then you find L. So, but I'm not explaining it well, but as we go along, you'd see, because obviously we need two masses to balance this. We can't just put one mass. And from that, you'll see mass on that side is equal to that, and yeah, you know where to position both masses. So obviously, don't want to talk too much. Straight into the example. And this is what it looks like. Obviously, it's not always put in a table for you, but hopefully it's put in a table so it's easier. But normally I have to read it and then obviously write it down. After this problem, I recommend you go to Kurmi and go do one or two examples, and then maybe a problem just to test to see if you understood what's going on. Right. So I'm not going to talk about the rotors and following properties, but it says it has masses, radiuses, as a stuff that you're used to, but now we have the actual distance from the first mass. That's important, and that is telling you how far away. Obviously, it's the sketch over here, the one here. I'll obviously put it up now. Exactly how it looks. And it says if the shaft is balanced by two counter masses, that's normally the case, located at 100 millimeters radii, just the radius, and evolving in planes midway of 1 and 2 and midway of 3 and 4. Determine the magnitude of the masses and respective angle positions. Stock problem. Standard. Right? Can't get more fun than this, but yeah, very good problem. Also test level like. Okay, so what I'm just gonna do now is obviously share my whiteboard and then attempt to solve it. Okay. Whew. Let's see. Where are we? Okay. So how does this look like, right? Obviously you want to sketch your space diagrams. That's the first one. You sketch your space diagram. It's summertime to record. I am recording. Yes, great. Whiteboard. So mass 1, mass 2 is 60. Mass 3 is 135. So this is, of course, looking at it from the front. It looks like this, like you're looking your eyes like this. I don't know if I'm making sense, but your eyes, you're looking at it front view. So I'll say front view. That's mass 3 and mass 4. There's mass 4. Oh, mass 4 is here. 270 degrees. Okay, I think it's the same as the previous one. I don't know if you noticed that. But looking from the side view, what am I doing? I'm trying to make an eye. Side view. someone's nose there. It's like this, and they state the position. So mass 1, we're going to start off with mass 1, because that's like at the 0 point. Then 160 millimeters away is mass 2. And then and the other one is 320. And the other one is 520. So I can 560, sorry. So I'm just gonna have it distances like this. 160. These problems can take a bit of time, but they normally they bulky marks, 25 marks as well. All the problems they're all big problems, not small Mickey Mouse problems. Anyway, you get the idea here. I don't want to still sketch all the lengths. And they said that the revolving planes midway, the balance, the counter masses, the balance masses is between 1 and 2, halfway. So half of this is 80. Sorry, I'll use a different color here. So that's we're gonna call it. They call it mass M. Right? You can call it anything on X or Y. Normally that's X. I think let's call it X. That's what you normally start with Y anyway. And then we can call this our other one Y, and the other one is between that. So from here to here, that's 80, and between these two, the distance between this two, obviously it's going to be the 560 minus the 320. So I'll just forgive me for not writing it down, and then just I think divide by 2 there, divide by 2. So that's 120 now. Right. Okay. So now what they want is the magnitude and determine the magnitude of the masses and the respective angle position. We don't know the angles, so we know where they must be placed, but we don't know at which angle and what is the mass we need to use. So does everyone understand the question so far? Can you see I'm looking at two planes here in a way? From the front view and then from the side view. Everyone still there? Thank you. I don't know if you guys tired now. Thank you. So, what did I say? Need update. Oh, we're going analytical, right? But we need a new table. Yeah, I think we don't have time for it. We'll continue with graphical again. But yeah, you guys need to make sure you guys do it. So we're gonna have plane, 1 column, mass, 1 column, radius, 1 column.
Sorry, sir.
Column. Yeah.
So can you please explain with the distance, the 8 and the 120?
It says if the shaft is balanced by 2 counter masses located at 100 millimeters radii and revolving in planes midway of planes 1 and 2, and midway between planes 3 and 4. So distance between plane 1 and 2 is 160. Between that is 80. You got it?
Okay, I see now.
And then if you look at planes 3 and 4, what I'm saying is that from 1 to 4 it's 560, and obviously from 1 to 3 it's 320. You subtract that 2, you get 240, which is 2. So 240 is between here and here.
Okay, okay, sir.
And between that is midway is 120.
Okay, thank you.
Yeah. So yeah, they go. You can obviously have now you need L, your M or L, And this is distance from the reference plane actually. So the reference plane could be a bit tricky. You have M or L, then you have your angle. What we just do now, just draw a lot of lines here. We have 1, 2, 3, 4, 5, 6, so it's 6 rows. So I'm gonna have to really forgive me here. So this will take a bit of time. I forgot that it doesn't take this much time to actually. Obviously, I'm demonstrating no problem here. So plane 1, and we're calling this X now. 2, 3. Oh man, we've got still 2 more to go here. They call it M and M, and I don't know why they left or right. I really don't know. I think it's left and they call it M and N. I just not sure exactly. So we have Y, we're calling it, and then 4. Okay. Right, we had an Excel spreadsheet. This is so nice. So 9 kilograms. We don't know MX. 7 kilograms. 8 kilograms. MY. We don't know what the mass is. Number 4 is 6 kilograms. Your radius, 0.1. We know this radius. It says also 0.1. Number 2, 0.12. Number 3, 1.14. It's 1.14, 0.14. This one is 0.1. They said it's this radius. Take 2 counter masses at 100 millimeters, and 4 we have 0.12. Okay, so let's work out our products. Can someone just write? Someone can just talk to me. So you see this the first. This is the static balance, right? Someone just give me the MR. So good static. This is the static part here. This part here. Static part of the table. Whereas this part here is the dynamic part. Well, the M or L, sorry. All right, so can someone just give me the MR product quickly? Just to get yourself busy here. Just in case you're sleeping. I was wait someone to shout it out for me. You guys in type rather. 0.9, yes. Keep going, 0.9. Sorry about that. 0.9. This is MX 0.1. Let's give us going there. 0.84, 1.12. Yep. That's good. 0.84, 1.12. MY, and this is going to be 0.72. Right. So this is the new part which you're unfamiliar with. So what we typically do, and I'm saying typically, it's not so simple what I'm saying, but normally in a case like this, right, we take our reference plane as this one here, by the X position mass, right? Mass X, this plane here. We take it from one of the planes. This is what normally happens. Not always, but that's what we do, right? It's going to take us too long to really do an investigation of all different planes and stuff, but anyway. So this will become 0, right? So this is now the 0 point. So what we do is basically L is a distance, the distances over here on our side view, so to say here. This one here, all those distances there. So the distance from X to 1 is negative 0.08. So anything going that way is 0.078, or negative. Everything going this way is positive, anything going that way is negative. I'm sure you could have taken, this is a reference plane, and then it'll be just a whole other setup. But anyway, I'm just letting you know. What is our second distance? Also 0.08, because it's exactly in between. Mass 3 is positioned from it's at 320, so 320 minus 80 should be 0.24. Mass Y is going to be 320 plus 120. Am I right? Oh no, it's what is this for? It's for something. What is mass Y? What's my length? Mass 4 is going to be 560 minus 80, 0.48. So what is my distance here? Can someone just help me? For mass 3, I have mass 3 already. Yeah, oh, mass Y, yeah, mass Y. Mass Y is MR of 0.1. What is my L here? What's my distance? 0.36. That is correct. Yep. Good. 0.36. Right. What we do now is find our M or L. I'm not including the, oh, we don't know the angles. Okay, we probably need the angles here. So obviously this is 0, angle M, we don't know, angle X, 60. I'm getting to the other stuff now. That angle Y, we don't know. We're looking for that into 70. And yeah, so now we have to times your MR by L to get your MRL, your couple polygon, your couple setup there. So can we quickly get that? So the unit here is kilogram meter, and this is kilogram meter squared. Just information sake, if you need to know. Yeah, it's not particularly important what you have. So can we get our M or L? So you want to take your MR times your L. So I'm just waiting on you guys now. I'm going to paste that as well. Okay. So I'm waiting on your okay guys, so you're just going to times 0.9 times 0.08. You should get minus 0.07. Obviously this is going to be 0. 0.84 times 0.08, that's 0.072. That times that, you should get 0.2688. In this case, that times that's 0.036 my, and that times that is 0.3456. Is there any questions thus far? Are we happy? Can we all populate this table? Students, are you still there?
Trying to follow, sir.
Yeah, okay. Is it too much for you guys or what? It's not that much. I'm just gonna push the analytical method, man. We'll do the graphical again. Yeah. So now let's quickly see. So this is what's important now. This is where we are. The dynamic balance, the conditions are the sum of MRs, M and MR here. It's a force balance, static, and this is the couple balance, is our dynamic count part of that. So what we have to do now is say, looking at the sum of MRL cos theta plus MRL cos theta And n obviously is not n, we have y. So you're normally going to find the y one first, like I said, before we get to the m. But you'll see what I mean. You'll see what I mean. So what we have to do, so what I'm saying here, let me get this right for you guys. Now I have to sum up all the M or L's here. So the first one is 0.072 cos 0, right? Just don't worry about this one yet. Cos 0. Following the angles now. And then we're going to do, obviously we're ignoring the x, we're ignoring the ones you don't have yet. You'll see what we're going to get there, don't worry. You add up the ones you have. This is plus 0.07672 cos 60, which is this. You do the 135 now, plus 0.2688 cos 135 tick, and then we're going to have the 270. Just bear with me here. That's going to be 0.3434. What's this? 0.3456 cos 270. Just this. Cos 270. And like I said, this one, it's not an x. This is now the this is this one here. Is my rainbow color. So M or L there will be plus, I'll write it here for you, 0. You guys can see the 0.036 cos. We had cos now. We had the y still. Yeah, I know it's rubbish. It's complete rubbish. I'll just make it a complete different color like this. 0. No, green. I was thinking green. So 0.036 cos. Oh, it's M or L. So it's we have. What's it? We have my, yeah. So my cos theta y. So I'm saying it's that over here, right? We don't know that angle. Coming to the x. So what we do now, guys, we have to sum up all of this. Sum up this guy and sum up that guy. All of those that fall, and it's equal to 0, right? Can we quickly get that value, the total value of that? Make sure you get it. Please do it. When we give for that value, cos 0 plus 0.0672. Yep, minus 0.22847. That is definitely correct. Obviously, what we do now, we can carry this over here, and it'll be equal to this. But obviously, here we have two unknowns, right? So what we do now is sum of the M or L sine theta plus exactly the same as it's M or L. So that's just the other condition now. M or L sine theta. This is all for the y. So obviously this guy we have already. Mr. Green here, 0.036 sine theta y. We equal this to 0. As you can see, we end up having two equations, two unknowns. So this is in equation 1. Oh, this is a mistake here. I carried this over there. So let's just sum up. You can just literally type this out on your calculator. So it's all the same values, 0.072 sine 0 plus 0.072 cos 60, etc., etc. You can just continue with that. So can someone just give me the total value here using sine? Well, we're not nearly there, but yeah, well, we're going to get there. Mr. Kiefer, you got it for us?
Yes, I get negative 0.09733.
Beautiful. Yep. Negative 97333. Then you have another equation, equation 1, for equation 1, equation 2. So I'll just put it up next to each other. So this one is 0.9733 equals 0.036 sine y. Equation 2, 0.22847 equals 0.036 or 6 cos of angle y. I'm just going to call it y here. Let me just call it, it's going to confuse people. Crazy stuff. And of course, what you can just do is divide. So what they do, they square these values. You can obviously square these values if you want. But, sorry about that. So it's equation 1. So what you can just do is divide. You can divide 2 by 1. So you can have tan y equals 0.0 divide. They square those values, so you can do that as well. But I just prefer the dividing way. It's just more quicker. Let's just get that angle. So Kiefer, can you just find the second function of this? Let's get that angle. You could have also, what you could have done as well, or you could have said your M or L in the y direction is just 9733 squared plus you're basically taking that to here, but obviously I'm using a different setup here. 47 squared. You could have done that as well, but I'm just going the other way. So what is my angle over here? Should get 23 point something. No man, it's not. That's not right. No, I must have zero. I must have zero. It's my fault. It's remember it's 0.00. You see 0.00. Man, yeah. Yeah, you get 23.074. Yeah. Yep, there we go. Degrees. Okay. So obviously, then what you can do now is, sorry, I missed something. I mean, missed something. This supposed to be, oh yeah, I have it the M cos, yeah. So now we can go back to equation 1 and 2. I should have had this. What I don't have here is the M, the my. Sorry. Back to equation 1, which is 0. Yeah, I think I have to call it today because it's a bit of an overload. 0.22847. That equals 0.031. And now we know the angle. Obviously, the angle is cos what's it now? 23,074. And obviously there's an MY here. This is what I'm talking about. And this is not 0,1, it's 0,36. Yeah, remember this is this here is 0.036 MY because of that angle. Of course, so I'm just making aware. This stuff is lekker. Anyway, now we can just simplify MY, and MY will be 0.2284. You could have also taken the tan of this and stuff. You'll see in the thing. 0.036 times cos of 23.074. If you get that, what's the mess? Moment. What mess do you get? Let me corroborate my answers here. 6,89825. Who's got this answer? Yep. Okay, guys. So what we've done now, we've characterized the position of this guy. Very easy. This guy. You know its mass. So if I could just make a plane for you. What's at angle 23? So what I'm saying is that this guy is gonna sit. Technology is beautiful. No, the color pen. I'm obviously extending. I'm exaggerating the radius. So that's 6.898 kilograms, and we got to put it at an angle of 23,07 degrees. That's only for MY. Okay, guys, what's next? We have to do MX, but we will not do it now. You can obviously check your notebook or the notes I've posted for you. I will explain how to do MX. I will obviously go over it for you, but now, just to let you know beforehand, you and I have to now go to your MR polygon now. So you just take the sum of MRs now, do exactly the same thing, and then you'd find your X. But obviously not MRL now. You start with your couple. You do, instead of MRL, you do MR for the force balance, and then you'd find MX. Would there be a problem using more than two countermasses? You probably could. I mean, it's just that I guess it's hard for me to when I'm talking through the analysis. But for sure you can. Let me just think about it. If we do that, right? Oh, there's a problem using more than two countermasses. No. I don't think so. No, it's normally two countermasses. Yeah, it's kept simple. If you check Kurmi, you'd notice like on the reciprocating side it gets a bit crazy. But the thing with this stuff is that depending how far I'm going to go, obviously I'll let you know, determine the scope of the lecture. Instead of you finding masses, you have to find angles and lengths, and it plays around with a thing. Instead of finding angles, you have to find lengths. You know what I mean, or the distances between the two planes. There's some variations within the problems, man. If that makes sense. But even this itself is a good exam problem. It just depends on my mood, Like I might give you a horrible one, or you might just get. But this is still within itself difficult because I mean, look at the amount of time it takes to like solve the problem. So yeah, it's challenging by that. So guys, when we get back next week, I'm gonna have to continue with this. I want to finish this problem, do a graphical method, I'm gonna have to do probably 1 or 2 problems if I can, and I have to make sure I show you the clutch problem as well, which I wanted to show you. I won't forget. I think obviously it's there. I've posted everything on Blackboard, so I'll just do the clutch problem. There's a little piece of mind to make you guys aware of, and maybe there's any understanding or lack of, or the nerves with the basically the dynamic problem. But what I recommend is going over the notes, just finishing up the example. I'll go over it again. I'll do the graphical approach. I have to lecture the thing. Obviously, we can do it. And then I'll take 2 problems maybe, and I'll just do them. And then we're basically done with balancing. So yeah, it's just I know it's a lot of stuff we've learned today. And Wednesday is always a hectic day for us. I think Friday is a lot better. Thursday is a lot easier. But anyway, guys, thank you for attending. I enjoyed today's lecture. I would like to finish it, but obviously we still have time. And by next week, balancing will be done, and then we start a velocity analysis maybe next week as well. Yeah, and I'll probably even though next week's the last week before break, but when you return, you have more month periods to finish up that 3rd chapter. Because you need at least 3 chapters to write the test, not just 2. But okay, guys, thank you. Hope you enjoyed today's lecture. Hope it was fun. Hope it was challenging. And see you on Friday for thermos. And be safe. Cheers, guys.